Hey guys, welcome back to another video. In this video, we'll be talking about the extreme value theorem. Alright, so let's get right into it. Okay, so I'm just going to start with what the extreme value theorem says. Alright, so extreme value theorem, also known as the EVT. So it basically says that if f is a continuous function on some closed interval a to b, right, then f attains a global maximum and minimum value. Okay, so basically we have some function f and it's on continuous on some closed interval a to b. So the extreme value theorem basically guarantees that f has a global maximum and a global minimum value, right? So what's a global maximum and global minimum value? Well, basically all it is really just like a maximum minimum value, but global means that it's like greater than all the other f in this interval. So for example, like the formal definition or semi-formal definition of a global maximum is if f of c, so if f of c is a global maximum, so f of c is a global max, then f of c is greater than or equal to f of x for all x in a to b. All right, so basically like, and obviously c is also in the interval, excuse me, a to b, right? And the global minimum has a similar definition. That's just like f of c is less than or equal to f of x for all x in a to b, right? So yeah, but basically that's what the extreme value theorem says. Okay, cool. And so like graphically, you can think of it as sort of, so if you have like, so say this is a and this is b, right? So you can have like some function, let's say it looks like something like that, right? So this is f of x. So then note that we have this closed interval a to b, right? And f is continuous, right? So roughly, so a continuous function that's roughly speaking, loosely speaking, that you can like draw the graph without lifting your pencil, right? And then a closed interval is just closed interval, right, to be, right? So then as you can see, f has its global minimum value or minimum value at a, and it has its maximum value at b. So in this case, this was a special case where the extrema, right, occur at the endpoints, but obviously it could occur within the interval too. So like for example, if we have like another example of the extreme value theorem, so let's say this is a, this is b again, and so it could look something like this, where, right, so now instead, let's say this is x1, so now uh, f of x has its global minimum value at x1, and then let's say that this x value right here is x2, so it has its global maximum value x2, and so then now it's no longer at the endpoints, it's within the interval, right? All right, cool. So now let's move on to some vocabulary. So we already covered the definition of what a global max and a global min is, right? Basically just like the maximum value of f over the whole interval. So, and global min is like the max or is the least minimum value of f over the whole interval. So then we also have the notion of a critical number, right? So we have a critical point, right? So we say that a point C is called critical if f prime of C equals 0 or f prime of C is undefined. All right. So f prime of C is equal to 0. What does that mean like graphically, right? Well, if you remember the definition of the derivative, it's just that the slope of the tangent line at x equals c. So if f prime of c is equal to 0, that means that the slope of the tangent line at c is 0. And so that means that it's a horizontal line, right? A horizontal line has slope 0. So again, if we have like some graph, let's just say like looks something like this, okay? And so let's say x equals c is right here. So this point right here. So notice that the tangent line to this is horizontal, right? But what is this also? This is also, so if we consider like this interval right here from a to b right here, let's say we have this closed interval, right? So now we have a continuous function on a closed interval. So by the extreme value theorem that we just discussed, this function, whatever it's called, let's say it's like y equals g of x. So g of x is guaranteed to have a minimum and a maximum value. So notice that at c it has a minimum value because the slope of the tangent line right here is 0, right? Or it just happens to be that the slope of the tangent line is 0 and is also minimum value. And then similarly, the maximum value, we can all agree, occurs over here. So I'll just call this like d, let's just say, occurs at this point. And like, look, guess what? The slope of the tangent line at d is also equal to 0. So basically, what I'm trying to say is that the minimum and maximum values of a function only occur at the critical points of the function. Okay, so I guess you could call this like a theorem or whatever, but like if g has a max or min value at x equals c, then c is a critical point. Right, and all that means is that g prime of c is equal to 0, right? But up here we have that a point is critical if it's equal to 0 or if the derivative is undefined. So when's the case when the derivative is undefined? Well, consider the absolute value function, right? So if we have the absolute value function, we have, looks like that, right? So this is y equals absolute value of x. So then note, look at x equals 0 right here. Here the derivative isn't defined because as you approach 0 from the right hand side, right, as you approach it this way, you get a tangent line equal to 1, right? It's equal to this. But then as you approach 0 from the left hand side, the tangent line is equal to negative 1. So the right and the left hand limits don't exist, or like are not equal to each other. And so therefore the derivative at x equals 0 for so I'll call this f of x equals absolute value x. So then f prime of 0 does not exist, right? So that's another example of a critical point. And the reason being because note that at 0, the absolute value function does have a minimum value, right? So therefore, this goes back to this thing where if f has a minimum value, then the x value where it has the minimum value or maximum value has to be a critical point. Okay. So yeah. Okay, cool. Now that we got that out the way, let's do some examples. So basically the critical points, just like derivatives, just basically express the idea of minimum and maximum values, like extrema, in terms of like slopes. All right, that's really all it is. But moving on to example 1. So we wish to find the global extrema if it exists. Okay, all right, part A. So let's say we have some function f of x equals x cubed minus 3x squared plus 1, and we're looking on the interval -1 to 3. All right, so the first thing that we have to ask ourselves is, well, does this function even attain a maximum or minimum value? Does it even have any global extrema on this interval? Well, the extreme value theorem will guarantee it, but only if f is continuous on this interval. So is f continuous on -1 to 3? Well, it is. And how do you know? Well, you could just take the limit as x approaches c of f of x, and c is simply any point in this closed interval. So it could be like 0 or like -1, whatever. So if you take the limit as x approaches c of f of x for c in this interval, you would get f of c, right? It's just equal to the function evaluated at c. And so this is the definition of continuity. So therefore, f is continuous. So then the extreme value theorem guarantees that f has a global min and max. All right, so by EVT, f has a global min and max on the interval. I should mention that. All right, good. So now how do we find it, right? Well, remember that a function, so f only has global extrema at its critical points. So we must find the critical points of f. So the critical points are simply where the derivative of f is equal to 0 or it's undefined, right? So let's begin by finding the derivative of f. So f prime of x, that's equal to 3x squared minus 6x, right, by the power rule. And so we can set this equal to 0. And now we just simply solve this equation, and whatever x values we get are the critical numbers. So we can factor out a 3x, and we're left with an x minus 2. So therefore our critical numbers, Cn, critical numbers, are x equals 0 and x equals 2. All right, cool. So now a common mistake that a lot of students make is that they will just evaluate the function at x equals 0 and x equals 2, their critical numbers, and then they would just like write whatever they get as for those values as a global min or global max. But actually, we have to remember that f can also have its extrema at the endpoints of the interval, right? Because we're only looking at an interval right now. So therefore, we must evaluate f at not only the critical numbers, but also at the endpoints. Because remember, we saw that example for the extreme value theorem where the minimum and maximum values were actually at the endpoints, not in the interior of the interval. But basically what we do is we simply are just going to make a list of all possible x values where the extrema could exist. So obviously we have our critical numbers 0 and 2, but then we also have to remember to include our endpoints, -1 and 3. And sometimes there's even cases when you don't get any critical numbers, right? Like it's never equal to 0 and it's like the derivative is never undefined. But then EVT does guarantee the existence of extrema. So then you're just like stuck. You're like, what do I do? The endpoints, right? But anyway, and we'll see that in the next example. But if we evaluate f at 0, let's see, we get 1. And then f evaluated at 2 is -3. F of -1 is -3. And then f of 3 is 1, right? So in this case, even if you did by chance forget your your endpoint, you'd still get the same maximum value values, but this is purely just a coincidence. All right. So we can say that f has a global min of -3 and global max of 1 on this interval -1 to 3. Okay, good. All right, good. Let's do another example. All right, so now let's say we have f of x equals 2 over x minus 4, and we're looking at the interval from 0 to 5. All right. So remember, the first thing we have to check is if f is continuous on this interval 0 to 5. Well, note that f of x has a vertical asymptote at x equals 4, right? And x equals 4 is in this interval. It's in 0 to 5. So therefore, f is not continuous on 0 to 5. So f is not continuous on 0 to 5, right? Because you have that vertical asymptote at x equals 4, so that's a discontinuity. Well, that's okay. Let's just see what happens if we restrict our interval. Let's say 0 to 3. So now is f continuous on 0 to 3? Well, f still has the vertical asymptote at x equals 4, but now that falls outside of this interval 0 to 3. So therefore, f is continuous on 0 to 3. So therefore, the extreme value theorem guarantees the existence of a global maximum and a global minimum on this interval because f is continuous on the closed interval. So now, how do we find it? Well, we simply find the critical points of f, and then we just evaluate f at the critical points plus the endpoints. Don't forget the endpoints. All right. So let's find the derivative. F prime of x is equal to negative 2 over x minus 4 quantity squared. All right. So to find the critical points, so first we're going to set this equal to 0. So set equal to 0. But then we realize that this equation right here, negative 2 over x minus 4 squared equals 0, that has no real solutions. All right. But it's okay. We're not done yet, right? Because there's another case. F prime of x may just be undefined. Right? Because if we find some x value for which f prime of x is undefined, that also counts as a critical point. So is f prime of x, which is equal to this, is that undefined anywhere? Well, we do have a vertical asymptote again at x equals 4. So this f prime of x, we do have a vertical asymptote at x equals 4 again. So we get that x equals 4 is when f prime of x is undefined. However, we were looking at the interval from 0 to 3, right? So is x equals 4 in this interval? No. So therefore, this is kind of like you can think of it as an extraneous solution. You don't care about this because it's not in our interval that we're interested in. So therefore, f prime of x, or like f of x, doesn't have any critical numbers, at least on this interval. So then what do we do? Does that mean that f doesn't have a global min or global max? Well, no, obviously not, right? Because the extreme value theorem said it did. So then what do? We have to evaluate f at the endpoints, guys. Those are the only 2 points left where f could possibly have a global min or global max. And indeed, that's where it's going to occur. So we evaluate f at the endpoints. So when x is equal to 0 and x is equal to 5. So, or sorry. We're looking at this new interval. So when x equals 0 and x equals 3. All right, so when x equals 0, f of x is equal to negative 1/2. And when x equals 3, f of x is equal to negative 2. All right, so then from here, it's clear that f has a global min of negative 2 and global max of negative 1/2 on the interval 0 to 3. All right, good. All right, let's do one more problem like this. All right, part C. So now, let's say we have some function f of x again, but this time it's given by 2 sine x minus cosine of 2x. Okay, and we're interested on the interval from 0 to 2 pi. All right, good. So again, first step in all of these types of problems is if we have to check is f continuous on this interval, because only then can the EVT guarantee that f actually has global extreme. Well, 2 sine of x equals a minus cosine 2x. Is that continuous on 0 to 2 pi? It is. How do we know? Well, we just simply take the limit as x approaches c of f of x, where again, c is some point in this interval. And you will always get that this is equal to the function evaluated at c, just equal to f of c. And so this is the definition of continuity, and so therefore f is continuous. All right. So then the extreme value theorem guarantees that f has a global maximum and a global minimum on this interval. All right. So now how do we find them? Well, first we just have to find the critical points of f, right? Because remember, like the critical point is where the slope is 0, which is when you have a like when you have an extrema, or when the slope is undefined, as we saw in the absolute value function. The slope can be undefined there, but you still have an extreme. So we're gonna find f prime of x. So this is 2 cosine x minus 2 sine 2x, and this is when you have to remember your trig derivatives, remember your derivatives for sine and cosine. And so first we will set this equal to 0. And let's see, what do we get? Well, we have cosine x equals sine of 2x. And so we're solving this equation on the interval 0 to 2 pi, remember, because that's the only interval we care about. And we solved a bunch of these types of equations in pre-calculus. So if you don't know how to solve this type of equation, I recommend you check out my video on it on my pre-calculus channel, on my pre-calculus series. But we've already covered this type of equation here on this channel, so I will just tell you what the solutions are. So you get that x is equal to pi over 2, 7 pi over 6, 3 pi over 2, and 11 pi over 6. And if you're just like having some difficulty solving this, I'll give you a hint. You should use the double angle identity for sine. All right. But these are the critical numbers that we get for f on this interval 0 to 2 pi. But we're not done finding the critical numbers yet, because we also have the case where f prime of x could be undefined. However, is f prime of x undefined on this interval anywhere? No, because f prime of x in this case is a continuous function, although that may not always be the case. But in this case, f prime of x is continuous on this interval 0 to 2 pi, so therefore it is not undefined anywhere. All right, so these are all the critical numbers that we have. So now we must evaluate f at all of the critical numbers plus the endpoints. So let's go ahead and do that now. So we have our endpoint of 0, and we have our critical numbers pi over 2, 7 pi over 6, 3 pi over 2, 11 pi over 6. And then finally we have our other endpoint of 2 pi. Okay. So f at all these values. So f of 0 is -1, f of pi over 2 is 3, 7 pi over 6 you get -3 over 2, at 3 pi over 2 you get -1, at 11 pi over 6 again you get -3 pi over 2, and then at 2 pi again you get -1. Alright, so from these values it should be pretty clear that f has global min. So f has a global minimum value of -3/2 and has a global maximum value of 3, right? On the interval 0 to 2 pi. Alright, so there you have it. Alright, so that pretty much wraps up this video on extreme value theorem. Basically, this is just like an introduction to finding extrema on an interval using derivatives in calculus, which is like a super big topic throughout the series, alright, throughout this course. Alright, so if you enjoyed this video and you found it helpful, please make sure to leave a like, and don't forget to subscribe. I'll see you guys in the next video.